Let us begin by understanding something about insurance premia. Obviously, we are talking in the context of risk. Uh, you are aware that for getting insurance cover, the insured has to pay a premium, which is in a sense the price paid for acquiring the insurance cover. The insurance premia are not actuarially fair. As you are aware, there is actuarial science which is based on the probability of risk. This is because of two reasons. The first reason is that administrative costs also have to be met out of the premia which have been obtained or got from the insured. And secondly, apart from the administrative expenses that have to be recovered, there is also another problem that the premium should also contain a return to the company, to the insurance company or the insurer. This return has to be equal to the opportunity cost of earnings, which are equal to the return on the next best alternative earnings of equivalent risk. This makes the return greater than what it would have been if the opportunity earnings had been risk free. Therefore, when we look in the context of a risk ridden economic environment, then these are some of the implications, and the economics of insurance is not straightforward. In other words, the return includes not just the compensation for the use of the funds of a particular use like insurance, that is, the insurer has to make a choice between investing the funds in the insurance business as compared to some other business. But not only that, the return should be equal to the opportunity cost, but it should contain some kind of compensation or in fact some reward for undertaking such risk. This implies that the insurers are also risk averse. They expect a certain return for undertaking such risk. Now, let us go ahead and see if there is any way in which the premium to be paid to be less actuarially fair and therefore lower. That means that is there a case for lowering the premium? In other words, can the reward for risk taking be removed from the return that the insurer requires to remain in the insurance industry? This is the question to be explored in this module. In particular, the effects of spreading the risk over a large number of insured would also be examined. This will be followed by an exercise to see how risk pooling can reduce the risk. So, there are many insured who are facing a certain risk, and the insurance company takes over, the firm takes over the risk, and in this context we would like to see what is the relevance, what is the significance of risk pooling. This module draws on what is learnt in module 30, and it is strongly recommended that you go through module 30 before you try to understand what is given in this.
In this module, you will learn that the risk to an individual sharing in a risky prospect diminishes as the number of individuals sharing the risky prospect increases, or that as the risky prospect is spread over a greater number of individuals, the risk to a particular individual diminishes. Similarly, if risk-averse individuals were to pool risky prospects which are not perfectly positively correlated and then share the proceeds, the risk to them individually would diminish. In order to examine the effects of spreading risk among individuals, a hypothetical example may be considered. It is assumed that the insurance firm is owned by a number of shareholders who, in the ultimate analysis, can be thought of as being the agents that are offering insurance. Each of these several shareholders gets a proportional share of the returns of the insurance firm. The income from insurance will be the premium charged by the insurance firm minus the compensation paid out. Since the compensation may be assumed to be probabilistic in nature, then for a given amount of premium received, the income from insurance too may be considered to be probabilistic. However, the stochastic nature of insurance is idiosyncratic. Insurance that is offered against damage arising out of events such as fire and accidents. These are idiosyncratic in the sense that these events are not correlated with events that affect the incomes of the individuals from other sources, such as recessions and booms either of the economy or sections of the economy. The income derived by the shareholders from other sources would therefore not be correlated with the proportional return from the insurance firm. In the analysis that follows, it is assumed that the income of the shareholders from other sources and the proportional return from the insurance firm that a shareholder gets are uncorrelated. To simplify the analysis, it is further assumed that the income from other sources is riskless. It shall be assumed that there is no asymmetric information between the insured and the insurer firm and between the insurer firm and its shareholders and therefore its owners. A share of value S would, in the absence of risk, yield in perpetuity in each period an amount equal to SF, where F is the risk-free rate of return on shares. This implies that buying a share by paying S is equivalent of paying an amount P equals SF in each period in perpetuity. Individuals, each of whom is assumed to have the same income from other sources and the same degree of risk aversion, can be thought of as each buying one share of the insurance firm by paying an amount P in each period. These are simplifying assumptions. Buying of shares by individual shareholders implies, in the ultimate analysis, that each is offering insurance to the extent of his share. In other words, it amounts to several small insurance providers acting through the medium of an insurance firm. Individuals will buy shares if the proportional share of income that they get from the insurance firm is greater than P. The total income I accruing to the shareholders of an insurance firm is stochastic, with its expected value assumed to be equal to expected value of I. Its probability density function is assumed to be defined entirely by its expected value and variance. Since the income from insurance is probabilistic in nature and hence has an element of risk, its certainty value for a risk-averse shareholder is less than its expected value of I. This requires a positive inducement to persuade the risk-averse agents to buy shares of an insurance firm. Shares will be bought by a rational individual under conditions of perfect competition if and only if 1 upon n is greater than p by an amount delta, where delta is the loading factor required to induce a risk-averse individual to participate in the insurance scheme, and n is the number of shareholders. A loading factor is an amount that is required to compensate the risk-averse individual for the risk taken in buying one share of the insurance firm. Where there is risk, the value of the loading factor delta must be positive. That is, delta is greater than 0. The income that an individual gets by buying one share of an insurance firm and thereby participating in insurance is given as delta equals to I upon n minus p. In this module, the conditions are overly restrictive or strongly stated because it is implied that each individual has the same utility function and the same degree of risk aversion. This assumption is a useful simplification and does not take away much from the essence of what is sought to be said. Since the total income from insurance I is stochastic in nature, it can be expressed as I equals EI plus U, where EU equals to 0. The maximum amount that all the shareholders taken together will pay will be given by NP equals to N into I upon Ni minus delta equals to I minus N delta. If the stochastic nature of the income from insurance were to be taken into account, then in terms of expected values, this may be expressed as NP equals to EI plus U minus N delta. However, since delta equals to EI upon N plus U upon N minus P, it is a function of N, the number of individuals participating in insurance. Consider the variance of I upon N. Recall that I equals to EI plus U. From this, it can be seen that I minus EI equals to U. This can be rewritten as I minus EI equals to U minus EU, since EU equals to 0. By squaring the expressions in the curly brackets and taking expectations, the equation can be written as E into I minus EI square equals to E of U minus EU square. This gives the equation of the variance of I as variance of I equals to variance of U. From this, it can be seen that variance of I upon N equals to variance of u upon n equals to I upon n square into variance of u. This shows that the variance decreases as the square of n, and in the limit as n becomes infinitely large, the variance becomes zero. Consider the income of an individual who has bought a share in the insurance firm. His income will be given by the sum of income from other sources and the income from insurance. These two incomes can be added because they are not correlated. This combined income will be y plus I upon n minus p. And since this amount has a stochastic element, namely I, and since there is a probability density function defined about I, the expected value of this will be E of y plus I upon n minus p. However, in any one period, the actual income that an individual will get will vary about this expected value. What is known is the probability with which the individual's actual income in any one period will be of any particular value. This is because there is a probability density function defined over all such values of actual incomes that may actually occur. Each of these incomes is associated with a unique value of utility. Hence, the probability density function defined over the various levels of utility that are associated with the levels of actual incomes that may occur is the same as the probability density function of the occurrence of the levels of income that could occur. This implies that it is possible to calculate the expected value of the utility of the risky prospect of participating in the operation of the insurance firm. If it is assumed that the individuals are risk averse, the utility function will be concave with respect to income. That is to say, that utility will increase with income at a decreasing rate. Under these circumstances, the expected value of the utility of incomes, which are the sum of incomes from other sources, and the incomes the risky prospect of participating in the insurance firm, will be less than the utility of the expected income from participating in the insurance firm, besides getting a certain income from other sources. In other words, E of u into y plus I upon n minus p is less than u into E of y plus I upon n minus p. Consequently, the certainty value of the income associated with the same utility level as the expected utility associated with the incomes that an individual could get by participating in a risky prospect, besides getting a certain income from another source, would be less than its expected income. It is this that gives rise to the risk premium that an individual would be prepared to give to avoid this risk, and hence gives rise to the positive value of delta. It was seen earlier that the value of delta varies inversely with the number of participants. As the variance about EI becomes smaller with an increase in the number of participants, the difference between U into E of y plus I upon n minus p and E into U of y plus I upon n minus p will become smaller and in the limit will equal 0. This, in a perfectly competitive environment, will reduce the value of delta to 0 when n becomes very large. Hence, spreading of the shareholding of the insurance firms over a very large number of shareholders ultimately implies spreading the insurance activity over a very large number of insurers and makes I upon n equals p in the absence of administrative costs. This makes the participants in the insurance firm behave as if they were risk neutral, even though individually they are risk averse. Consequently, the insurance premium in the absence of administrative costs and the income from participation in an insurance firm yields a return that is equal to the risk-free return and becomes more actuarially fair. In the presence of administrative costs, it becomes less unfair. Now, let us learn about risk pooling. An alternative to reducing risk faced by an individual is by increasing the number of participants in any risky scheme by pooling of risks. Risk faced by individuals can be reduced by pooling, provided their incomes are not perfectly positively correlated. This can be understood by means of a model of two individuals with identical Newman-Morgenstern utility functions, which are concave with respect to income. Identical Newman-Morgenstern utility functions are a simplification. The concavity of the utility functions of the two individuals indicates that they are risk averse. Simplifying assumptions are made that both these individuals face identical risky prospects, which involve either getting an income of Y1 with a probability of P or getting an income of Y2 with a probability of 1 minus P. These two individuals get into a pooling arrangement wherein they pool their individual incomes and share the sum equally in each period. The possibilities of incomes received by these two individuals simultaneously and their respective probabilities are given in the table. It is to be noticed that the occurrence of the incomes for the two individuals is not correlated on a one-to-one basis. If individual 1 were to get Y1, individual 2 may get either Y1 or Y2. Similarly, if individual 1 were to get Y2, individual 2 may get either Y1 or Y2. If the occurrence of the two incomes were to be perfectly correlated, so that if individual 1 got Y1, individual 2 too would get only Y1, and if individual 1 got Y2, then individual 2 would also get only Y2. Then pooling would not reduce the risk to either individual. Now let us consider the utility that an individual derives from the risky prospects without and with pooling. If the individuals do not pool their incomes, the expected utility that an individual will derive will be U1 equals to PUY1 plus 1 minus P of UY2, where U1 represents the expected utility from a risky prospect without pooling. With pooling, the expected utility of an individual will be U2 equals to P square UY1 plus 2P of 1 minus P into U of Y1 plus Y2 upon 2 plus 1 minus P square UY2, where U2 represents the expected utility from a risky prospect with pooling. Individuals will opt for pooling if U2 exceeds U1 or that U2 greater than U1, which implies that U2 minus U1 is greater than 0. Consider the difference between U2 and U1. It is equal to P square UY1 plus 2P into 1 minus P into U of Y1 plus Y2 upon 2 plus 1 minus P square UY2 minus PUY1 minus 1 minus P of UY2. P square minus P into Uy1 plus 1 minus P square minus 1 minus P Uy2 plus 2P into 1 minus P into U of Y1 plus Y2 upon 2. This simplifies to P of P minus 1 into Uy1 plus 1 minus P into 1 minus P minus 1 into Uy2 plus 2P into 1 minus P into Uy1 plus Y2 upon 2. This simplifies to 2P into 1 minus P of U into Y1 plus Y2 upon 2 minus P into 1 minus P into Uy1 plus Uy2, and further simplifies to 2P into 1 minus P into Uy1 plus Y2 upon 2 minus 1 by 2 of Uy1 plus Uy2. Consider the expression in the square bracket. For a concave utility function, it is positive.
Let us now summarize what has been said in this module. Insurance is not actuarially fair, not only because the insurance premium has to cover the administrative costs, but also because it has to meet the opportunity cost of the resources, the funds which the insurer is investing in the insurance business, and therefore, it should include an element of reward or compensation incentive of some sort for undertaking such a risk. The risk faced by the insurance company is certain idiosyncratic factors, and it is not related with the systematic risk that firms face in the economy. As you are aware, there are two types of risks, systematic and unsystematic. Systematic risks are those risks which all firms, all companies in the whole of the industry face, whereas unsystematic risks are those risks which are peculiar, which are idiosyncratic to particular firms. It can be then assumed that the income received by the potential shareholder from other sources is uncorrelated to the income they would receive from the insurance companies as their share of the insurance firm's income. Imagine each shareholder as being a provider of insurance working through an insurance firm. each shareholder would require a return from the insurance to for the inducement to buy the shares of an insurance firm. As the number of shareholders increases, the variance of income is about to expected value to become smaller, and so does the size of the return required from the insurance to induce the shareholders to participate in insurance. In any competitive environment, the return is this inducement, and the inducement will tend to 0 as the number of shareholders become indefinitely large. In other words, they behave collectively as risk neutral, even though each of them individually is risk averse. This is the effect of spreading risk. Another device to reduce the risk for risk averse agents is the pooling and the sharing of risky prospects. This reduces the risk to any individual risk averse agent, and provided that the pooled incomes are not perfectly correlated.